am Snigdha Bharadwaj, Assistant Professor, ITS College of Pharmacy. Once again, I welcome you all in my presentation. So, in this presentation, we are going to discuss about one compartment open model of intravenous bolus administration. So, let us get started. So, one compartment open model intravenous bolus administration. So, we have discussed in earlier sessions about the compartment models, how we consider compartment body as a compartment. So, in this we are going to discuss one compartment open model. One compartment means we are considering body as a single compartment. So, if we give the drug through intravenous bolus administration or we give through IV administration a drug. So, how it is perform or behaved within the body and how the pharmacokinetic parameters are affecting drug performance. So, this model will give you the brief about this total pattern of the drug, how the body parameters are affecting the drug performance. So, when a drug that distributes rapidly in the body is given in the form of rapid intravenous injection, that is IV, bolus or slug, it takes about 1 to 3 minutes for complete circulation and therefore, the rate of absorption is neglected in calculations, right. So, when you see that if we give intravenous injections to any patient, then the effect will be very quick. So, in that case the rate in availability is minus rate out. So, rate in availability dx by dt, the rate of absorption. So, is written like rate in and rate out. The elimination is availability minus elimination. So, since the rate in or absorption is absent in IV bolus, the equation becomes dx by dt, rate of absorption is equal to rate out. Means, if we take a tablet orally, we say that first the tablet is getting disintegrated, then dissoluted and then absorption through the lumen will take place and then it is going to the blood. But when we give or administer drug through IV injections, we say that no absorption is taking place, only distribution will take place directly. So, that why rate in availability or absorption will be neglected in this particular case and only rate out will occur. So, that why this equation becomes dx by dt is equal to rate of absorption is equal to minus rate out. So, if the rate out or elimination follow first order kinetics, as we say that in compartment model and model dependent approach, the kinetics can be identified using first order kinetics. So, dx by dt will become k E x. So, k is equal to the constant of first order kinetics, where k the first order elimination rate constant and x is equal to amount of drug in the body at time t remaining to be eliminated. As we considered that the drug is entering through IV administration directly into the blood circulation and it is not getting absorbed from any particular barrier, it is directly entering to the blood, right, through IV injections. So, only the elimination phases will occur at that point of time. So, replacing that rate out with the first order kinetics, we say that the first order elimination rate and x, the amount remaining to be eliminated, because it is already entered to the body blood circulation and slowly immediately or slowly, we can say depending on the drug's nature, it will be getting eliminated through the system, right. So, negative sign indicates that the drug is being lost from the body. So, basically the negative sign is generally depict that the drug is eliminated from the body. Okay. So, estimation of pharmacokinetic parameters in using this one compartment open model in IV bolus administration. So, for a drug that follows one compartment kinetics and administered as rapid IV injection, the decline in plasma drug concentration is only due to elimination of drug from the body. So, when we follow one compartment kinetics and administered as rapid IV injection, the decline in plasma drug concentration is only due to drug elimination from the body. Yes, because absorption is not taking place, it is directly reaching to systemic circulation. So, it is quickly distributing all over the body and then eliminated, right. So, and not due to distribution, the phase being called as elimination phase, right. So, that only due to elimination, this elimination phase can be characterized by 3 parameters. So, mainly our focus is to analyze the elimination parameters if we give dose or a dose of a drug through IV administration. So, elimination rate constant we can identify, elimination half life and clearance, because there is no absorption taking place in IV bolus. So, we are focusing on elimination phases, elimination phase related parameters like elimination rate constant, elimination half life and clearance. So, first is elimination rate constant. So, using that particular earlier equation you see here, dx by dt is equal to minus k E x. So, we use elimination rate constant, we can calculate integration of this equation, integration equation x is equal to integrated x naught minus k E t. If we put integration of this equation where x naught amount of drug at time t is equal to 0, that is the initial amount of drug injected. So, how to find out elimination rate constant? If we use this equation in the exponential form as x naught e to the power minus k E t, and log form log x is equal to log x naught minus k E t divided by 2.303. So, after solving these particular equations, and last we can say that we can get this log equation, and since it is difficult to determine directly the amount of drug in the body x, it is very difficult to determine the amount of drug in the body x. Advantage is taken of that fact, a constant relationship exists between drug concentration in plasma C and x, that x stands for amount of drug in body and C stands for drug plasma concentration. So, we can say that it is very difficult that directly amount reaches to the blood is identified, identification is very difficult. So, we basically what we do, we can establish a direct relationship of the drug with its plasma concentration and the presence of body in terms of volume of distribution. So, whereas Vd is apparent volume of distribution, it is a pharmacokinetic parameters that permits the use of plasma drug concentration in place of amount of drug in the body. So, using this equation we can easily calculate that particular elimination, how much drug is present in the body and how much is to be eliminated. So, using that this equation log, so we have put that Vd is the apparent volume of distribution. So, we consider as is equal to C. So, instead of in this equation instead of x we use C. So, log C is equal to log C naught k E t 2.303. The elimination rate constant is directly obtained from the slope of the line. It has unit of minutes inverse 1, right. So, thus minus to the power 1. So, thus a linear plot is easier to handle mathematically than a curve, which is in this case will be obtained from a plot of concentration versus time on regular plot. So, basically the linear plots are comparatively easier than a curvy one, but in this case we will obtain from plot concentration time profile curve, right. So, here you see the volume of distribution is like it is also an important parameter, and we put C equals to x. So, this equation becomes log C is equal to log C naught minus KET divided by 2.303, and you see here the plots will we will get through this equation is the concentration time profile curve. So, two types of plots are there, we generally get regular Cartesian plots and semi logarithmic plots. So, in this case you see the linear lines obtained in semi logarithmic plots, because we have taken log concentrations, log value of the concentrations, and you see the different time intervals are known as this, the 50% time is T half. So, T half basically T half, and in this semi logarithmic the log 1 and log C 1, log C 2 different concentration in blood plasma, right. So, slope value is this, and using this equation we can calculate our drug amount present in the system. So, first is Cartesian plot of a drug that follows one compartment kinetics given by rapid IV injection, whereas in semi logarithmic plot for the rate of elimination in one compartment model. Generally, for identifying rate of elimination we use this plot. Okay. Second is elimination half life. So, also called as biological half life. Elimination half life is also called as biological half life. It is the oldest and one best known of all pharmacokinetic parameters and was once considered as the most important characteristic of a drug. So, basically it is an important parameter, and it was we can say that the most important parameter to identify the drug characteristics. It is defined as the time taken for the amount of drug in the body as well as plasma concentration. It is defined as the time taken of the amount of drug in the body as well as blood plasma to decline by 1/2 or 50% of its initial value, right. So, the time taken to reduce to its 50% ratio of the 50% of the initial value in the blood plasma and in the body, we generally termed as T half. The how much time drug is getting reduced by its 50% to its initial value is generally termed as biological half life and T half of the drug. It is expressed in hours and or minutes. Half life is related to elimination rate constant by the following equation. That means, elimination phase is also depends on the half life of drug. The higher the half life, the elimination will be we can say that it will take longer to remove from the system. So, T half is equal to 0.693 by Ke. So, clearance. Third point is clearance. Clearance is defined as the theoretical volume of body fluid containing drug from which the drug is completely removed in a given period of time. So, basically clearance is the clearance of the drug amount from the body. So, it is a theoretical value of body fluid containing drugs. So, we analyze hypothetically that the different compartments have different body fluids containing drug amount and how much time it is taking to get cleared from the system. So, which the drug is completely removed in a given period of time, it is expressed in ml per minute or liters per hour. So, both the values units can be taken. Clearance is usually further defined as blood clearance CLB, plasma clearance CLP, or clearance based on unbound or free drug concentration, right. So, CLU, right. So, depending upon the concentration measured for the equation. So, blood clearance, the clearance from blood and plasma concentration refers CLP, clear based on unbound or free drug concentration CLU. So, depending on the concentration measured for the equation, we can use this particular equation. CL, rate of elimination, divided by plasma concentration dx by dt divided by C. So, you know that the elimination rate is referred as dx by dt and divided by C. C stands for plasma concentration. Now, area under the concentration time curve, AUC calculation, area under the curve, right. Basically, two methods are available, model dependent and model independent, to analyze the drug concentration in blood, right. So, model dependent can be used only for one compartment IV bolus, and model independent can be used for any drug with any route of administration, because it does not consider body as compartment, is just use the concept that the drug is showing the linear kinetics in the when administered in the body. So, it can be used for any drug with any route of administration, right. So, we have discussed these model dependent and independent approaches in the earlier sessions. So, you can have a look. AUC calculation through model dependent approach. If we talk about that, for IV bolus we can use this model dependent approach. So, with one compartment model, first order elimination and intravenous drug administration, the AUC can be calculated using this formula, like AUC is equal to dose by K dot Vd is equal to C naught by K. So, basically K is your absorption constant, dose given, Vd volume distribution. So, dose, that means the concentration of drug in plasma is equal to C naught by K is your absorption rate constant. So, AUC calculations, if we talk about that trapezoid rule, we have discussed in our earlier sessions. So, to identify model independent or calculate model independent approaches in physiological models, how we calculate? We will use this model dependent approach using this trapezoidal rule. So, you see that the curve AUC area under the curve calculation with one compartment model, first order elimination and intravenous drug administration, we can use this AUC calculation. So, you see that this is your concentration axis and this is your time axis. In earlier we have read all the time profile curve, concentration time profile curve. So, this is an example of that, how to calculate. So, you see, divide the area into different part based on observed concentration. That means, at point of time the Cmax was this, then reducing time by time. So, we have based on the time intervals, we have categorized our area as 1, 2, 3, 4 and 5 and more, right. So, next calculate the area for each part of the parts 1, 2, 3, 4 until the last observed concentration using trapezoidal rule. So, this one box is known as trapezoid. So, this is how we use trapezoidal rule to calculate AUCs or to calculate the pharmacokinetic parameters. So, using these trapezoids as and consider it as boxes 1, 2, 3, we will calculate area under the curve. How? Right. So, we have segregated these boxes. Now, for part 5, area between the last observed concentration and infinity, use following equation. So, for that particular trapezoid, area is equal to C2 plus C1 by 2. Yes, this is C1 concentration and now it is getting reduced after t time to C2 and then reduced to C3 and changed to C4, C5. So, C1 and C2, T2 and T1 and T2 at point time T and T2. So, you see the equation will be followed like area C2 plus C1 divided by 2 dot T2 minus T1, where C is your concentration and T is your time profile. So, when we measure all these points, right. So, for part 5, area between the last observed concentration and infinity, use the following equation. When you see that further no reduction is seen or no further area is seen. So, you consider it as infinite point and you take this particular equation to calculate the area of this part 5, C asterisk divided by K. So, this is how the total area will be calculated using this particular equation. Fourth, the total AUC from 0 to infinity, 0 to infinity can be calculated using the sum of the areas of part 1, 2, 3. That means, you are using this equation to calculate individual area, but for this area you are using this equation because further no we can say that area will be continuing. So, or concentration will be seen. So, using this equation and the results obtained from these equation for part 1, 2, 3, 4 respectively and for this equation for 5, you will sum up all the AUCs and you will get the AUCs from point 0 to infinite point. So, this is how you calculate area under the curve using this trapezoidal rule, and this trapezoidal rule basically is used effectively for identifying AUC. So, fraction of the dose remaining, how it is calculated? Fraction of dose remaining F is equal to x t by x 0 is given by following equation at time t and at time 0. So, F amount at time t divided by dose. So, this can be represented in this particular formula or equation, and T half is equal to 0.693 by K. The equation after putting 0.693 by K instead of T half, we can have this equation fraction of dose remaining. Using this we can calculate F is equal to 6 minus point in power is equal to half T by T half divided by T half in power. So, using this formula we can calculate fraction of dose remaining. So, these are different factors we can calculate for using that particular calculating AUCs, fractions, amount of drug eliminated, time to get to certain concentration. So, using this T is equal to, so all these equation will be obtained once we calculate the AUC part. So, we have different concentration and different time readings. So, we can put all these readings in this particular equations to get different parameters. So, integration C asterisk divided by K. So, through this, so certain concentration is given by what concentration is pending or remaining within the system, we can calculate. Applications of one compartment model, predicting plasma concentrations, duration of actions, value of dose to give a desired initial plasma concentration. So, basically for identifying plasma concentration and area under the curves, we have studied this one compartment models. So, once again I will highlight what are the things we have discussed. So, IV bolus one compartment open model, in this we have identified basically no absorption is there. So, only elimination phase will be given consideration, and for that elimination rate constant and elimination half life and clearance will be considered to calculate the drug profiles within the body. So, eliminated rate constant and this two plots can be plotted using these regular plots and semi-logarithmic plots. Basically, semi-logarithmic plots are used for identifying rate of or plot rate of elimination of the one compartment models. after elimination half life. These are also known as biological half life, in which time of course, the drug is reduced to 50% of its initial value is known as half life. Clearance, basically blood clearance, unbound drug concentration clearance, plasma clearance. So, these all are terms which can be calculated using this formula, and model dependent approaches using this trapezoidal rule. So, I have discussed in detail how to calculate using that individual trapezoid, right, to calculate total AUCs, and these are fractions calculating of the dose remaining and then concentration and applications. So, this is very important to identify area under the curve, duration of drug action, and the dose required to give into a patient at particular interval. So, I hope you understand all the concept of one compartment open model for IV bolus administration. In next slide, we will be continuing with the IV infusion administration. Till then, take care and stay safe.